Good morning, everyone. So I'm Yohan PERCHER from Chantier de l'Atlantique, and I'm going to present you the topside general arrangements and outcomes of the semi-submersible floater design analysis. I will start with a short presentation of the company, and then I will present the topside general arrangements, followed by the semi-submersible floater design, and I will finish with some conclusions. The Chantier de l'Atlantique is one of the major shipyards in Europe. It's located in the city of Saint-Nazaire in the west coast of France, and there are 10,000 people working on site. It's composed of 3 business units. The first one is about the constructions of cruise ships and military ships. The second one is for ship maintenance. And there is Atlantique Offshore Energy, which is our business unit dedicated to the construction of electrical offshore substations. We have supplied substations for many wind farms across Europe, including most of the wind farms in France, and also in the North Sea and in the Baltic Sea. And our first HVDC substation is entering into construction this year for the wind farm Centre-Manche in the north of France. I'm going to present now the work done about the topside general arrangements. The topside is the upper part of the substation, the lower part being the floater. And the objective of the topside are to host the high voltage and the auxiliary equipment for the 2 gigawatt HVDC application. And it should be compliant with the electrical architecture. The challenge here is that we change the scale in mass and volume, because today most of the substations are with alternative current technology, and with direct currents, the volume and rates are multiplied by a factor of about 10. And the study also includes a structural verification for the different phases, like lifting, towing, and also for the in-place configuration. The philosophy we have adopted for the construction is that we want to limit the dimensions to make the topside buildable in Europe. Building the whole topside in one block is not compliant with the yard's facilities because of its large weight and its large volume. And this is why we have adopted a modular approach. And this is made possible by the fact that many of the high voltage equipments are repeated 4 times. So we have split the topside into 4 modules. The advantages of this approach is that one module is compact and adapted to the European supply chain. It's easier to build, to install. And when we build them in series, there will be an associated cost decrease. However, there are a few implications with this approach. We need nearshore works for module interconnections, and the overall weight will be a bit larger than a topside in one block. There has been some reflection on the philosophy for the transport installation, and a scenario was proposed. So thanks to the modular approach, each module weight remains below 6,000 tons. And for example, the largest heavy lift vessel in the world is called the Sleipnir, and its maximum capacity is 20,000 tons. But it's a vessel very expensive and not always available. So having smaller modules means that we can use smaller heavy lift vessels, which are less expensive and maybe more available. So in the proposed scenario, we would build the topside modules in Chantier de l'Atlantique and the floater in a shipyard in Europe or Asia. We would tow the modules and the floater to a sheltered area. We took the example of the Brest Bay, Brest being a port in Brittany in France. Then we lift the modules on the floater and we tow the substation to a deep water quay for intermodular connections. Again, it would be possible in West Polder. And we tow the substation to its final location and we commission it. So here is described the topside. The different rooms hosting the high voltage equipment have been distributed into the 4 modules. So you can see in the table, most of the high voltage equipment are repeated 4 times. The modules are made as similar as possible and symmetric. And we have integrated the auxiliary systems into topsides. There is the HVAC system, which means here heating, ventilation, and air conditioning. There is also cable routing, safety rooms, cranes. There is a heli deck and boat landings. And there is also a living quarter for 48 people, which would be used only in case of emergency. And on the bottom right figure, you can see the location of the eye tubes. So the eye tubes are the vertical tubes that receive the electrical cables. So 16 of them are represented with the green circle and are for the inter-array cables coming from the wind turbines. And 3 of them, the red ones, are the export cables. One for the positive pole, one for the negative pole, and one for the neutral that go to shore. The resulting topside properties are provided here. So the outside length is 129 meters. The width is 64 meters. There is some spacing between the modules for access, for stairs, and for lay-down areas. And the total mass of this topside is 21,500 tons, and this is quite large for comparison. The typical weight of HVAC substation is for the topside is below 3,000 tons, and typical length is 40 meters. So HVAC topside is about half, just one module. That's it for the topsides. So a second task in which we participated is the design of the semi-submersible floater. So in this project, AFOSS-DC, 2 different types of floater were studied and sized for the defined topside. So there is first the semi-submersible that I'm presenting and the tension leg platform that will be presented next. And these are 2 typical types of floater commonly used in the offshore industry. So the objective is also to design the corresponding ring systems and cable configurations. And we have defined criteria to make the floater buildable in shipyards. And we have chosen maximum width based on a dry dock called Form B in Chantier d'Atlantique. So the maximum width corresponds to the corresponding maximum width is 58 meters. We also have to fulfill stability requirements from standards. And another important criterion is the acceleration limit defined to protect the electrical equipment. So we have defined the maximum allowable accelerations of 4 meters per square second in horizontal and 3.5 meters per square second in vertical. And finally, we have to check wave clearances. So we have 2 criteria for this to ensure that there will no be wave impact on the topside bottom, neither on the floater bottom, on the floater keel. We have considered as inputs the 100-year return period storm, representative of the Atlantic coast, the associated maximum significant wave height is almost 14 meters, and the wind speed is 28.5 meters per second. And we have studied 3 water depths for the mooring system. So here is presented the resulting submersible floater, which is composed of 6 octagonal columns linked by pontoons. There is a transition piece in red that you can see in the figure, which links the topside to the floater. The overall length is 130 meters, the width is 74 meters, and the height is 35 meters. The central columns are a bit wider to host the eye tubes for the electrical cables. And you have to note that the width of 74 meters for this floater is larger than the criteria of 58 meters that we have fixed, which means that we cannot build this floater in the dry dock Form B of the Chantier de l'Atlantique, but it's still buildable in other shipyards in Europe and Asia. So the in-place draft is 20 meters. The draft is a bit lower for towing to facilitate the towing. And yeah, all these dimensions and drafts have been defined to find a compromise between all the criteria. We will find in these tables the final masses and the results of the motion analysis with this floater. So the weight of the whole floating system is detailed in the top right table with a total mass of 64,000 tons, with 1/3 for the topside, with almost 16,000 tons for the floater, and 40% of the total is due to ballast. So we have these ballasts are composed of seawater that are located inside the pontoons in order to reach the target draft of 20 meters. In terms of hydrodynamic behavior, which is interesting to see that wall and pitch natural periods are above 23 seconds, which is above wave periods. So the waves will not excite much the wall and pitch motion of the floater, and the resulting wall and pitch motions shown in the bottom left table. So they are quite limited. They reach maximum 5 degrees, which is well below the criteria that we have fixed of 15 degrees. And the associated accelerations in the topside are also below the criteria, with a maximum 2 meters per square second. And in the bottom right table, you see the criteria for wave clearances, and they are both satisfied with a small margin of 24 centimeters that show that the floater is quite optimized. Here I presented the mooring systems. The work was done by France Energy Marine, and they designed 6 different systems for 3 different water depths. So they are each composed of 4 clusters of each 3 mooring lines, so 12 mooring lines in total. You can see in the middle figure a profile of 1 mooring line. So there is a long section in this one of steel cable, that's the section in blue. And at the bottom, there are sections in yellow, in red, of chain with clump weights, that's the black dots, clamped to the chain that provide a catenary behavior to the mooring line, and that helps lowering the maximum tension in the line. In the 6 mooring systems, 4 of them consider polyester instead of steel cable, because it's an interesting synthetic material, which is cheaper. And in the end, the 6 mooring systems, they all satisfy the criteria provided by the standards, and they all comply with the procurement capabilities from the industry. And the cost assessment has been initiated to compare those 6 mooring systems. And for each mooring system, the inter-array and export cables have been designed. So we reach here our conclusions. So we are very satisfied of the AFOSS-DC work and results because a large amount of data were produced during these 3 years of projects through simulations and testing. All criteria fixed initially have been fulfilled, which is very satisfying, except for the hull brat, but still the floater is buildable in other shipyards. So this project was for us also a good opportunity to progress on the general arrangements of the topside for the floating application. And in the end, we achieved a major step towards demonstrating the feasibility of this future substation.